Hello learners, welcome to Dr. D.Y. Patil Vidyapeeth's Center for Online Learning. I am Professor Dattatray Katore and you are studying with me statistics and quantitative techniques. In this video, we are going to learn queuing theory. So in queuing theory, we are going to understand single server model and multi-server model. We will be learning the concept of queuing theory and its applications in business situations. So this is unit 11 of your course, statistics and quantitative techniques. So what exactly queuing theory is? So queue is a line of people or vehicles waiting for something. So it can be a line of objects, line of elements which are waiting for the service. So in many business situations, people have to wait for the service, right? In a bank also, when we go to bank to withdraw cash or to transfer some payment, then also we have to stay in a queue, in a system, in a bank for some time. If we visit a doctor, then also we have to wait outside at the reception before we get service. So there are many business situations such as transportation. So many business situation involves queues, and therefore management of such queues is very important. Management in the sense we should be able to utilize the servers properly. We should be able to decide the number of servers so that the service or customer satisfaction is not affected. So these kind of things are involved in queuing theory, and therefore queuing theory is very important to understand because it has applications in many business situations. So queue is basically line of people or units which are waiting for the service. Then queuing theory involves mathematical and statistical tools, statistical models which help us to understand the mean service rate, the arrival rate, right? So these kind of things. Structure of a queue. So a queue consists of a server, then there is a source of origin or input source where the customers or units originates. They move towards the service for the service. They stay in a queue for some time. They get service from the server, and when they get service, they exit from the system. So in a queuing theory, there will be some customers who will be in the queue, and there will be some customers who are being served. So the total number of customers in the queuing system will consist of the number of customers who are in the queue as well as the number of customers in the number of customers who are being served. So this is it. Then we have two terms such as waiting time in the system and waiting time in the queue. So waiting time in the queue means average time spent by a customer in a queue, and waiting time in the system means total time spent by the customer in the system. So this includes the time spent by the customer in a queue as well as time of service. So input source, then there is a queuing discipline, and then there will be a service facility, and when the customers get service, they exit from the system. But there are some customers who do not want to stay in the queue, such as booking customers and reneging customers. So let us have some understanding about these customer behavior. So customer behaviors, booking of queue. So some customers decides not to join a queue due to their observation related to the long length of queue. So people may think that the queue is so long and therefore they may exit from the queue. We also often, when we go to bank or when we go to a doctor, and if there is a very long queue, then we decide that not to remain in a queue because the time required to get service will be very high and we might not be having that time at that point of time. So then there can be insufficient waiting space or improper care. So if you go to a doctor or a bank and if there is no place to sit, so if there is insufficient place, then also you do not want to remain in a queue. Also there will be improper care, so while customers are in the queue, so if there is not proper care when the customers are in the queue. Nobody asks them, then they are customers, they can leave from the system. They can move to some other bank also. If we are talking about banking customer, when we talk about the hospitals, so if you do not get the proper service, you can change your doctor, you can change your bank. So this is balking, and thus pertains to the discouragement of customers for not joining an improper or inconvenient queue. Then there are reneging of queue. Reneging pertains to impatient customers. So after being in a queue for some time, few customers become impatient and may leave the queue. So there are customers who remain in the queue for some time, but after certain time they feel that they are spending too much time, and that's why they decide to quit the queue. So this phenomenon is called as reneging of the queue. Then there are some customers who are called as jockeying customers. So we who jump from one queue to another queue. So these are jockeying customers. There are some impatient customers also who do not want to stay in the queue, and they start fighting for the service. Characteristics. So the queuing theory is characterized by arrival process, the rate at which different units or customers arrive to the server or system. So this is arrival process, and in general the arrival process or arrival rate follows Poisson distribution. Then there is a service process. So the rate at which service is imparted to different units and customer is the service process or service rate, and this service rate follows exponential distribution. So these are some probability distributions, each of which with different properties and characteristics. Number of servers. So number of servers available to serve the customers. Number of channels. So there can be a single channel model, there can be independent channels, there can be multi channels. Then number of phases and stages in queue. So there can be a single queue or multiple queue, right? So the arrival rate is lambda. So the total arrival rate will be the addition of the arrival rate of both queue. Then series or tandem. So there can be servers who will be serving these queues in tandem simultaneously. Then there can be a cyclic network, queuing discipline, selection of service. So there will be some rule according to which the customers coming to the server will be served, and the more general rule which is followed is first come first out. Importance of queuing theory. So improve customer service continuously. So a business firm can improve the customer satisfaction and customer service continuously by managing the queue properly. Because in a banking system also, in a doctor also, healthcare service also, in many situations people have to wait for the service, and if they have to wait for a longer time, then there will be the satisfaction will be affected. So the managers of the firms have to take decisions such as how many servers should be there, what is the peak time, what is the service rate, what is the utilization factor. So what is the they have to look at the cost as well. So all these things are considered, and a proper decision is taken regarding the queue and service. So that's why queuing theory is very important, because a firm can improve the customer service by using the concept of queuing theory. When a system gets congested, the service delay in the system increases. So when there is a congestion, the delay will increase. So one need to understand the relationship between congestion and delay. A good understanding of the relationship between delay and congestion is essential for designing a proper queuing system. A queuing theory provides all the tools needed for this analysis. Queuing models calculate. So what we can calculate from the queuing models? So we can calculate the average number of customers in the system waiting and being served. So we can calculate the average number of customers in the system. So average number of customers in the system includes the number of customers who are in the queue as well as the number of customers who are being served. Then we can calculate the average number of customers in the line or queue. So the number of customers in the queue is denoted by WQ. Right, so let me write down the notations as well. here. So average number of customers in the system is denoted by LS, so length of system. So this means that how many customers are there in the system. So this includes the number of customers who are in the queue as well as the number of customers who are being served by the server. Then this is LQ, average number of customers waiting in the line. So number of customers waiting in the queue only. So LS is greater than LQ because LS includes the number of customers who are being served along with LQ. Average time customer spent in the system waiting and being served. So this is WS. So WS is the total time spent by the customer in the system. So this includes the time spent by the customer in the queue as well as time spent by the customer while receiving service from the server. Average time a customer spends in the waiting line or queue. So this is WQ. So time spent by the customer in a queue. So this does not include the time spent by the customer while receiving the service. So this doesn't include the service time. Then probability that there is no customer in the system. So one need to understand whether the system is idle or not. So we have to calculate the probability that the server is idle, that is there is no customer in the service center. So this is denoted by rho 0. Probability that there are n customers in the system. So this is denoted by rho n. And utilization rate, the proportion of time the system is in use. Right. So this is utilization. This is denoted by rho. This is probability n, Pn, not rho n. So probability that there are n customers in the system is denoted by Pn. Assumptions in queuing theory. So different for every system. So queuing theory, there are many variations in the queuing theory, and according to these variety of queuing theory and models and system, there are different assumptions. Variable service times and arrival times are used to decide what model to use. So the probability distribution followed by the arrival rate and service rate determines the model. Queuing theory is not a complex problem. So queuing theory is not intended for complex problems. We have seen this in class. We have already understood, and it is there on your Swayam portal as well as. So where there are many decision points and paths to take, and this can become tedious, confusing, and time consuming, and ultimately useless. Examples of queuing theory. So outside customers. So commercial service system, barber shop, bank teller, cafeteria. These are some examples of outside customer service centers, service system or queuing systems. There are transportation systems. So often we have to wait in a queue to get a ticket, right? So traffic lights. So we have to wait in a traffic until we get a green signal. Social service system can be judicial system, healthcare. So there also we have to stay in a queue until we get service. And then there can be production lines. In production lines, so different jobs have to wait before they get served on different machines, before they get processed on different machines. Terminology involved in queuing theory. So there are customers. So independent entities. Customers are the independent entities or units that arrive at random time to a server and wait for some kind of service, then leave. So customers are the units or entities. They are independent. They arrive randomly, and they arrive to the server to get the service. When they get service, they exit from the system. Server can only service one customer at a time. So server can serve a customer, only one customer at a time. Length of the time depends upon the rule followed, right, and the service rate. The customer are served on the basis of first in first out, so FIFO, and time, real, continuous, and time. Queue. So what is a queue? Customers that have arrived at the server and are waiting for their service to start. So this is queue. Queue length at a time. So the number of customers in the queue at a time is the queue length. Waiting time, the customer has to wait between arriving at the server and before they get service. That is waiting time. Important characteristics. So arrival process, the probability distribution that determines the customer's arrival in the system. Generally it is Poisson distribution. Then service process, the probability distribution that determines the customer's service rate, and it is generally the exponential distribution. Number of servers, so amount of server available, the quantity of server available to provide service to the customer is the number of servers. So this is all about the terminology. Then measuring queuing theory performance, so we must understand and measure the performance of the queuing theory, and if the performance is not satisfactory, we should make some necessary changes so that we can increase the performance of the queuing theory, and by doing that we can improve the customer satisfaction. So average number of customers waiting in the queue or in the system, so we can find out how many customers are waiting in the queue, right? If this length is very high, then we have to modify the queuing theory, we have to add one more server. Average time waiting, what time a customer has to wait, right? Capacity utilization, what is the utilization factor of the server? Cost of capacity, so what is the cost of increasing the capacity? The probability that that an arriving customer will have to wait, and if so, for how long? So these kind of things we can know from the queuing theory, and we can take necessary actions so that we can improve the customer satisfaction. Three important assumptions in the queuing theory. The system is in a steady state. The mean arrival rate is same as the mean departure rate. Alright, so the mean arrival rate is same as the mean departure rate, and therefore the system is in steady state. The mean arrival rate is constant. This rate is independent in the sense that the customers won't leave when the line is long. So we assume that the mean arrival rate is constant. So if this is not so, the customers would be leaving the queue if the queue is so long. So we are maintaining that the mean arrival rate is constant. So it indirectly means that the customers do not leave the queue when the queue is long. The mean service rate is constant. So we are also assuming that the mean service rate is also constant. So if this is so, then the servers won't speed up their work if there are more customers in the queue is longer. Parameters for queuing model. So parameters includes lambda. So lambda is used to denote the mean arrival rate. Then as lambda is equal to mean arrival rate, that is the average number of customers divided by per unit time, then 1 divided by lambda will give us the mean inter-arrival time. So this will give us the mean inter-arrival time of the customer, time between their arrivals. Okay, so by formula we can check it. Lambda is equal to number of customers arriving divided by time, right? So 1 divided by lambda will give us the time divided by number of customers. So it means that it will give us the inter-arrival time, that is the time interval between the arrivals of different customers. Similarly, we have mean service rate, so average number of units that a server can process per period. So mu is equal to number of customers served divided by time, and therefore 1 upon mu will give us the mean service time. 1 upon mu is mean service time, and m is the number of servers. Parameters example. So we have an example here. So lambda is equal to mean arrival rate, that is 200 cars per hour through a toll booth. So there are cars who approaches a toll booth, and they have to pay the toll of road toll, let's say. So the arrival rate is 200 cars per hour. Now we have data. So if it takes an average of 30 seconds to exchange money at toll booth, so it takes 30 seconds for a server to serve a customer or a car at the toll booth. Then there is a mu, that is mean inter-arrival rate. So this is equal to 1 divided by 30 cars per second. So this is mu, 1 divided by 30 cars per second. So from this we can calculate that if one car is served per 30 seconds, then we can say that 2 cars will be served per minute, and from this we can calculate that 2 cars per minute means 120 cars per hour. Why we are calculating it in 120 cars per hour? Because the mean arrival rate is given per hour basis, and that's why we needed to calculate the service rate in per hour basis also. So Mean arrival rate is 200 cars per hour, mean service rate is 120 cars per hour. It means that when we divide lambda by mu, what we get is 1.67, and this 1.67 indicates that one server is insufficient to serve the arriving cars, and therefore you need to have two queues, you need to have two servers, so that you know uh, the things will be you know things will happen quickly, and the people can pay their tolls quickly and can go through the toll. Then performance measures, so there can be some performance measures such as system utilization. You can find out the proportion of the time that a server is busy. Then you can find out the mean time that a person or unit spends in the system, that is in queue or in a service. So system utilization, let me elaborate on this. System utilization is the proportion of the time that a server is busy, right? So that is server is busy. Then mean time that a person or unit spends in the system, we can calculate that. Then mean time that a person or unit spends in the spends for waiting for service. Then mean number of people or units in the system, mean number of people or units in the queue, and probability that there are n units in the system. So all these things can be calculated by using queuing theory. So these are some formulae to calculate the queuing theory, right? So expected number of customers in the queue, average waiting time in the system, average waiting time in the queue, then average waiting time for a customer, expected length of non-empty queue, probability that there are n customers in the queue, probability that there is nobody in the queue or system. So we have an example here. A service store employs one cashier at its counter. 9 customers arrive on an average every 5 minutes, while the cashier can serve 10 customers in 5 minutes. So we are given here the arrival rate as well as the service rate. The arrival rate is 9 customers per 5 minutes, and the service rate is 10 customers per 5 minutes. Assuming Poisson distribution for arrival rate and exponential distribution service rate. So we are going to use a model for this. Then find probability that a server is busy. We have to calculate the probability that server is idle. We have to find out the average number of customers in the queue in the system, average time customer spends in the system, average times customer waits before being served. So all these things we have to calculate. So probability that the server is busy is given by lambda upon mu, and we have already discussed that lambda is arrival rate. So lambda is arrival rate, and mu is service rate. Alright, so from this question we can know that the mean arrival rate is 5 minutes, 9 customers per 5 minutes, and the mean service rate is 10 customers per 5 minutes. So arrival rate is 9 customers per 5 minutes, and service rate is 10 customers per 5 minutes. So what does this indicate? The server will service rate is higher than the arrival rate, right? So there are chances that server might be idle. So let us find out this probability that server is busy. So this is equal to 5 will get cancelled, 9 divided by 9 divided by 10. So 9 divided by 10, that is 0.9, is the probability that the server is busy. So these two events are mutually exclusive. It means that the server will be either busy or idle. Both of these events cannot happen simultaneously. At the same time, server is busy and server is idle, we cannot say that. So server will be either busy or it can be idle. So rho 0 is 1 minus rho only. So rho 0 is nothing but 1 minus rho, right? So 1 minus lambda upon mu. So this is equal to 1 minus 0.9, and this is equal to 0.1. So probability that server is idle is 0.1. Then we have average number of customers in the system. So average number of customers in the system includes the number of customers in the queue as well as the number of customers who are being served, and this is equal to lambda divided by mu minus lambda. So let me calculate this. So this is equal to lambda is 9 divided by 5, per 5 minute, and this is 9 divided by 5, 10 divided by 5 minus 9 divided by 5. So this will be equal to 5 will get cancelled. 9 divided by 10 minus 9 is 1. Now let us calculate this thing also. LQ is equal to, LQ is the length of the queue, means number of customers in the queue only. So we are not considering here the number of customers who are being served. So this is equal to 9 upon 5 bracket square divided by 10 upon 5, and this is 10 upon 5 minus 9 upon 5. So these 5's will get cancelled. Let me elaborate on this. So this is equal to 9 upon 5 square, 9 square upon 5 square divided by 10 divided by 5 multiplied by 10 minus 9 is 1 divided by 5. So this 5 square and these two 5's will get cancelled, and this is equal to 81. 9 square is 81 divided by 10, so it is 8.1. So this is equal to 8.1. So 8.1 is the average number of customers in the queue, and 9 is the number of customers in the system. So LS is always greater than LQ, right? So LS means the number of customers in the system. So this includes the number of customers who are in the queue as well as number of customers who are being served. And the length of queue means, LQ means the number of customers in the queue only. Then we have average time customer spends in the system. So this is equal to 1 divided by mu minus lambda. So this is equal to 1 divided by 10 divided by 5 minus 9 divided by 5. So this will be equal to 10 minus 9 is 1. So this will be 1 divided by 1 divided by 5. This is equal to 5 minutes. Right? So 5 minutes, because this 10 divided by 5 is the mean service rate. This is per 5 minutes. 10 divided by 10 customers per 5 minutes. This is service rate, and 9 customers per 5 minutes is the arrival rate. So from this we can calculate the waiting time in the system. So the time the customers have to wait in the system. So this includes the time spent by the customer in the queue as well as the time spent by the customer while receiving the service. Then this is equal to 9 divided by 5, whole is divided by 10 divided by 5, 10 divided by 5 minus 9 divided by 5. So let us solve this. 9 divided by 5, right, divided by 10 divided by 5, and this is 1 divided by 5. So one of the 5 will get cancelled here. Alright, so let's calculate 9 divided by 5, 10 divided by 5 square. So one of the 5 will get cancelled. Okay, so I can remove it, and this will become 9 5s are 45 divided by 10. This is equal to 4.5 minutes. So this is equal to 4.5 minutes. So 4.5 minutes is the average time customers spend in the queue before they get service, and WS is the average time customer spent in the system. So this includes the time spent by the customer in the queue as well as while receiving the service, and WQ means the time spent by the customer in the queue only, and therefore WQ is always less than WS. So that's all about this particular queuing theory, and I hope you must have understood what is queuing theory and its application in business situation. So queuing theory is very important topic as it is applicable in many service sectors or service organizations. So thank you for watching this video, and keep watching further videos as well. So thank you so much.